All right, we're back and we are on page 3 of note 6, I think. Yeah, note 6 of Calc C. We're talking about comparison tests. And we just talked about the direct comparison test, assuming you're watching these videos in order. And now we're going to talk about the limit comparison test, which I much prefer to use. So limit comparison test, a little bit easier to use. You have to be good at taking limits, but you don't have to kind of like come up with your own sorry, this app updated like in the middle of me making videos, and now things are looking a little different. So that's kind of interesting. You have to be good at taking limits, but you don't have to establish that like your convergent series is bigger than the other series, or your divergent series is smaller than the other series. We're not going to need that for this, which is why I prefer this one. So this is test number 7. I don't know if I could rattle them off. Geometric series, telescoping series, nth term, integral test, p-series, direct comparison, limit comparison. Got them. Okay, limit comparison test. Here's what it says. So we need positive term series. Pretty much all of the tests that we know so far, except for geometric, I guess, need positive term series. So positive terms, and if the limit as n approaches infinity of a sub n over b sub n. So it doesn't actually matter which one you put on top. I usually put the one that I'm testing on top. So like the one that I'm given that says like, does this converge or diverge? I'll put that one on the top, but it doesn't actually matter. If that limit equals L, L has to be positive, which it will be because these are positive terms. So I'm not sure I've ever really understood why that one's there. And finite, so it can't be infinite. And it can't, well, positive, it can't be 0. Your limit cannot be 0. So positive and finite, if those things happen, then they both do the same thing. So they either both converge or both diverge. So what's going to happen is you want to pick a series that you know the convergence or divergence of, and then compare it to that. So what that means is you'll go with kind of like the standard series that you know, and those series are mainly p-series and geometric series. So I usually look and see if in this like perfect world scenario, is it basically a p-series? Is it basically a geometric series? Let's do some examples and see what I mean by that. So here we go. In a perfect world, this looks like the harmonic series where somebody just like shifted it a little bit to the left and then like multiplied a little bit, or actually I guess scaled it down. So I'm going to say that I'm going to compare this to 1 over n, right? Because it looks like 1 over n. You start with 1 over n, you multiply by 6, you add 8 in the denominator, however you're going to pull that off, and you just get the series we're looking at. This I know diverges. And so if I take the limit and I got a positive finite, I know that the series I was given also diverges. So let's take a look at the limit as n approaches infinity of 1 over 6n plus 8 over 1 over n, which is, so you can kind of do this however you want. N goes to infinity of n over 6n plus 8, which is 1/6, which is positive finite. So I'm going to say, since n equals 1, 1 over n diverges. So maybe I should say therefore, right? Because we did the limit, we got 1/6. Therefore, since this diverges, the given series also diverges, which is just like fantastic. I mean, it's so much easier. We didn't have to worry about like, honestly, like, so say you tried to do the direct comparison test, you'd probably also try to compare it to 1 over n. The problem is that 6n plus 8 is bigger than n, which means the reciprocal is smaller. So now it's smaller than a divergent series. The direct comparison doesn't work. The limit comparison allows you to avoid that issue. So I guess I should say by limit comparison test. All right, and the key here, or a key, is that this part, I hate when I like, you got to get in one shot. This is positive and it's finite. So as soon as that happened, we knew what was going to happen. As soon as we got positive finite, we know they do the same thing. So then the key is like, do you know what the original series does? That's going to be a big deal. All right, so when I look at this, let me just show you how I work out this. So 3n squared plus n over n to the fourth plus radical n. All right, so if n is enormous, if n is huge, then this part doesn't really matter, and this part doesn't really matter. They just don't really matter if n is huge. And then, so that means that this is approximately just 3n squared over n to the fourth. So I look at like the dominant term. If n is going to infinity, what is having the most impact in the numerator? What's having the most impact in the denominator? And just ignore all the other stuff because it's just going to go away. Well, it doesn't go away, but it just doesn't contribute a lot. So this is 3 over n squared. So what I'm going to do is I'm going to limit compare this to just the sum of 1 over n squared, because 3 over n squared, 1 over n squared doesn't really make a difference which one we use. We'll get a positive finite. If we get a positive finite, we'll get a positive finite no matter whether we use 1 over n squared or 3 over n squared. So I'm just going to use 1 over n squared. I know that this is this converges, which converges because p equals 2, which is greater than 1. All right, so now I need to do my actual limit. So I'm going to do the limit as n approaches infinity of 3n squared plus n over n to the fourth plus root n over 1 over n squared. So the kind of interesting thing is like you're forcing this to work. Like if you make the correct choice of what to compare it with, it's going to work out and it's going to basically do what you're comparing it to, right? Like 1 over n squared converges. This is going to converge. We just have to like show the work. And then I'm never really sure how much work to show. Because it's like the point of this isn't really to demonstrate your ability to take the limits. So here, I'm just going to say this is 3, because it is. You could like use L'Hopital's a bunch of times. You could divide 3 by the highest power of n in the denominator. You could look at it and just be like dominant terms, 3 over 1, 3. So this is positive and it's finite. So we can say, since the sum of 1 over n squared converges, like p equals 2, I guess, we know that the sum of, what is it, 3n squared plus n over, why so small, n to the fourth plus root n converges by limit comparison test. By limit comparison test. Okay, so what I'm going to do, what I'm going to stop the video here. I'll come back in the next video and do the rest of the problems on this page. So we're off to a good start. Limit comparison, I love using limit comparison. I think it's probably my second favorite test. My favorite test to use, we don't know yet, is the ratio test. That's my favorite to do the math on. Obviously, you want to look at a series and be like, oh, it's geometric or it's p-series. But failing those, you have to do something. Ratio test is my favorite. Limit comparison is far and away my second favorite. But anyway, I will be back in the next one, and we'll finish this page, hopefully, unless something goes wrong. So see you there.